Draw a sketch of what you think happens. Is he a soldier? He looks like a soldier. Over time. I love that some of you are being super perfectionists, trying to fix it so that it matches. How precise can you make it? Oops, sorry, I meant to hit this button so that you guys could go on to the next page if you wanted to. Remember, once you've got your graph, hit play on the video so that you can see if it matches it. And you should see there's a darker green guy that shows your path, and then the lighter green guy is the original. Okay, so we had some interesting things to talk about here. I actually didn't put one of the other graphs on there. But what would happen here? This is not her final answer, by the way. But what would happen with this graph? What would happen with the Cannon Man in this graph? He would shoot off into space. He would never come down, so he'd just be hanging there in the sky. Gravity would avoid him. He'd lose his family. He'd just be hanging there. Should we see what happens? Whee, no parachute. So remember, this is the guy. Oh, where'd he go? Remember, the dark one is the, should we watch it again? He was raptured. He obviously, he just disappeared. He's a poof. That's because he's no longer, it's not that he, if I add this to the graph, then he would still be hanging there. See, he'd be still. He's just hanging there. But when you take it off the graph altogether, it just poof, disappears. Had another thought. I can't remember where I was. Anyway, oh, I remember. What else can we say about this? What other change do we need to make to this graph? Obviously, we also need to continue flying the guy, but what else? What's wrong with that first section? He's too slow. He's too slow. He's more like getting, I don't know, levitating into space instead of being shot out of there. So what do we need to do? A steeper line. He needs to go faster, so we need to make it steeper so that his rate of change is faster. Yeah, good. Okay, let's look at this one. Watch what happens in this one. You tell me what's going to happen on this one, actually. He's going to fall too quickly. It's hard to tell. And die. What else? Anything else you want to add to that? And rise too quickly? Okay. Any other thoughts? I can't tell if you're still typing. Peak is too sharp. His impact would kill him. All right, let's watch. What else can you say now that you've seen the graph? Yeah, obviously too sharp, too fast. There were two of him. He comes out of nowhere. Were there two? He looked like he glitched. Right there. What about the starting point? When does he start? Somewhere right there. He starts too late, right? He starts way too late because the graph is over here instead of starting at time 0 when the story starts at time 0. So the graph should have started right here and then up. Why does it look like he glitched? It's like he's in two places at once. Why? The line's not straight. It's not a function. Why is it not a function? So partly because it's going backward, it's going this way, so it's like not straight like that. But it fails the vertical line test. Somehow he's magically up here and right here at the same point in time. In the same point in time. We have one input with two different outputs. That breaks all kinds of laws of physics that he's going to be in these places at one time. Thank you, whoever created that graph, for giving me that example to share with everybody. And then I want to talk about this one, Euphemia. Why can I never remember how to do that part? Okay. So I know what Euphemia was doing, which is lovely. I love this. But What kind of graph has these dots like this? Do you remember? Where they're not connected? Dots. It's a dot graph. I'm going to talk more about the dots and in a minute, but it's a dotted graph. It starts with a D. It's kind of scatter plot. You guys might have seen that in your, yeah. With the one where there can't be a half. Yeah, what is that called? The one where there can't be a half, where it starts with a dis. Ends with a crete. What is that? Discrete. Yes, with an E on the end of it. Yeah, discrete. A discrete graph where you can't have halves. You just have discrete points. But then Euphemia started to connect these. What's the opposite of a discrete graph where they're all connected? What do we call that? Disconcrete. Nope, it's not linear, but you're on the right track. Linear is just a straight line, but not all linear graphs are this. Not sloped. Starts with a C. See linear. I should put this over here so it's on my recording. Nope, you're on the right track. I know. Continuous. It's a continuous graph. You're not gonna get it. It's a continuous graph. And this one should be continuous, right? What would it look like if we left it discrete? Should I play it so you can, well, you tell me what you think it's gonna look like first if I leave it discrete. She was starting to connect the dots when I grabbed the screenshot of it. What's it gonna look like? He teleports from one spot to the next spot. So it's like a little funny. Let's see if that's what happens. Remember, the green guy is, you can't, it doesn't do it on Desmos, but yeah, he would be like here and then here and then here and then here. Yeah, you have to actually connect it to make it go it. And obviously, I think Euphemia realized that he's going a little too slow out of that. He needs to go a little faster. But the dots aren't a bad idea. Dots aren't a bad idea, so keep that in mind. And then I should probably show one that's an actual, well, you guys can see some better answers. Here's one. My computer glitched. It's trying to do too many things at once right now, but it's pretty close. It's pretty close. So he rises pretty fast and then he slows down his descent because of the parachute. Okay. All right, moving on. I'll let you guys move on to the next carnival ride. If you have not helped Alejandro, go help Alejandro fix his graph a little bit. And then you can go on to bumper cars. How did they create that straight line? It's still locked. You mean you want me to hit play? The part where I start yelling at you guys for not doing anything, and then it's because I've paused it. Bumper cars! On the bumper cars, the first question that you have to answer on slide 5 after 4, after you watch it, is what quantities might be interesting to look on a graph. So on the Canon guy, we looked at his height over time. What kind of things would be interesting on the bumper cars to graph? How many cars it hits? When you say hitting that drift at the bottom, I imagine you mean like the speed of the car. What other kinds of things? There's a number of different possibilities. Try to be unique, but also right. Some of you like to be super creative, but not necessarily in the right direction. Whee, parachute. Velocity, acceleration. So make a figure 8. Do you mean its position on the screen would be what you would be graphing? Its position on the screen, like how far it is from the bottom of the car turning. So which direction it's facing throughout the whole, like you could keep track of how it's turning. The speed versus the weight. How busy the graph is. Do you mean by how many cars are on the screen at any one time? Like by measuring, numbering, keeping track of the number of cars on the screen? Oh, I love that someone turned that question around into a sentence. So they said, I think the quantities would be interesting to look at would be the figure 8. Do you mean like you would graph its position on the screen? Perhaps. Yeah. Yeah. So you'd graph its path. Somebody's still on somebody's really trying to get their graph right. Somebody's a perfectionist on the Canon man. Now here's the key to these graphs when you start creating the graphs on 5 and on Alex, that one that's about narrative. There's a basic narrative and then there's an advanced narrative. It's all about what's on the x-axis and the y-axis. So all of those examples that you gave on 4 would be an excellent thing to keep track of, but here we're graphing the distance traveled. How far has it gone over time? Yeah, but your first graph was so good and I didn't even get a snap of it. And you scribbled all over it. and not share that screen though, because I really just want to show you this. Okay, there we go. All right, so this was the bumper cars. So this was exactly what I graphed. I'm not gonna lie, except I started here. I started up here and then graphed like that. But watch what happens on this one. Crash. And then it just disappears off the graph. So this person was graphing the position of the bumper car on the screen instead of the distance traveled. So you have to think as this is going, it's traveled like a foot and then 2 feet and then 3 feet and then 4 feet and then 5 feet. So a foot, 2 feet, 3 feet, 4 feet, what would that look like? Can I go? Ah, that's how I go back. Okay. And then this one, what is this graph going to look like? What is it? What's the bumper car going to do? It's too fast. It's going to stop. Where is it going to stop? When the line goes straight. So the distance is increasing, the distance it traveled is increasing here at one rate, and then it stops here for the rest of the time because at this point it crashed. Anybody else have anything to add to that description? So increasing constant. All right, so let's watch. Oh, crashed too soon. And then it stopped, and then it crashed. So it's too fast. So we need to make this less steep. So the line should be more like this, and then stop. Okay. And then we have this one. What can you tell me about this situation? It goes too high. Not a constant rate of speed because it's a little wobbly because they didn't use the line tool up here. So it's a little wobbly, so it's gonna slow down a little bit here. And it goes too high. What do you mean by it goes too high? The distance traveled is too much. So it's not gonna, this is where the crash happens, right? So the crash is gonna stop too far. Let's see. Oh, a little slow. Oh, that's pretty good. It's pretty good. Maybe just a little too high. Maybe a little too high. Yeah. Okay. One way to make this graph a little more precise is do what Florence was doing, and that is to periodically stop it. I think that's what Florence was doing, and put a dot there. Oops. Stop. Stop. It's easier when you don't already have a graph on there. And then put a dot. Let me erase this graph and start over again so I can show you. It's kind of cheating to do it that way, but you can do it that way. It's because I'm trying to record this at the same time that I'm, anyway, you can pause it and put a dot where it is, and then dot, and then dot, and then dot, and then connect the dots. All right, let's look at the, I'm gonna stop sharing for a second. Let's look at the Ferris wheel one. So here are different responses that I got to the Ferris wheel problem. So this is the classic, like, okay, I'm going to draw a Ferris wheel on this graph. But it's the height off the ground over time. So as you guys all alluded to, said, you can't be, the same cart can't be here and here at the same time. So this is not a function, and because this is a real world life thing, it's probably going to be functional. What happens in this graph up here? That looks a lot like the parachuting guy. Was the parachuting guy and the Ferris wheel the same graph? Yep. Goes the wrong way. So the height increases, which would mean that the cart is going up and then sitting still in the air for a little bit. It's floating in the top, and then it goes back down over time. Good. These two graphs are very similar. It starts and then it decreases, which means the height is decreasing. And if you think about what does it mean for the height to be decreasing, that means it's going down, it's going lower in the air. Doesn't go all the way down to the ground, because that would be the cart on the ground, and that would be bad probably. The cart was actually on the ground. And then the height increases. So when you're doing these kinds of things, think, okay, what does that mean for the height to be increasing? That means it's going up in the air and then it goes back down again. But what's the two differences in these two graphs, other than that this one is very like linear and this one's more curvy? Which one do you think matches better? Do you want to just see? Let's just see. So this is a curvy one. Well, it's pretty smooth. And then we have the pointy one. It kind of bounces. Bounce. So smoother would be better, but then you have a wiggly line and that's hard to do. But yeah, a little smoother curve to it, because there's a little, it's slows down a little bit at the top and then around. Okay, good. All right. We're going to stop this function carnival here, and we're going to go to a different function carnival now. Hopefully now playing around with that a little bit, you have a better idea of how to read graphs for their stories. This one we're going to do now is, the whole idea is that you are understanding how this is connected to function notation.